Perfect. Thanks for the lovely introduction. So my name is Victor. I'll be presenting indeed the Copernicus Global Land Cover and Tropical Forest Mapping and Monitoring Service. Now don't worry, that's a mouthful. For the rest of the presentation, I'll just say LCFM, because otherwise I would only be able to treat half of my slides. A bit about myself. I'm a data engineer at VITO in Belgium. I've always lived in Belgium. I love traveling, but sometimes I do need to be at home. As a job, I'm part of the data engineering team for OpenAO. I'll explain what OpenAO is thoroughly throughout the presentation. But I kind of try to form the bridge between the all technical stuff and the very smart biological researchers who try to do their research on remote sensing. So I'm kind of between both worlds. I keep on learning about all sciences, but as Gilberto said in his intro presentation, to the core, I am still an engineer trying to learn in order to build, working with all the smart scientists. As a quick overview of my presentation, I'll give you some background on previous products that have been released, and mainly the lessons learned we got out of these for the LCFM project. And then I also like to deep dive a bit more in OpenAO, which has been supporting the LCFM project quite a lot, and I think is a perfect topic for FOSS4G as well. So as most of you know, the global land cover data is often providing valuable information for decision-making, for research in the fields of biodiversity, food security, carbon assessment, and climate change. And one of these products is a product released by the European Commission by the European Environment Agency. It has been produced by a consortium led by VITO. And this is a 100-meter global land cover map. So it divides the whole world into, I think it's 23 classes. I know how fast you can count, but it is a discrete map. So next to this, we've also released, at a 100-meter resolution, a map containing 10 continuous cover fraction layers as well. So these contain, for this example, for example, shows in red the scrub layer, the tree layer in green, and grass layer in blue. So researchers can do a bit more of analog research as well instead of sticking to these discrete classes. Now, gaining feedback on these products, 100-meter resolution is great, but in the end, Sentinel satellites capture a lot of data on 10-meter resolution. So given that, in collaboration with ESA, we produced the ESA WorldCover at 10-meter resolution for the years 2020 and 2021. A little bit less classes, so these contain, I think, top of my mind, 11 classes. You might have seen this map earlier, this conference already in the presentation of Gilberto, perhaps not with the right connotation in my opinion, because this map has been proven useful for a lot of projects to start up the research, to divide land, to get some information on the fractions of land use within areas. But the feedback we got out of this is often researchers still want to do their own classification, and in the end they end up doing the land classification themselves once again. To give a quick example of these previous products, this is a lovely city of Antwerp, where I was born and raised and love living still. It's a false color composite. And here in the center you see quite a lot of buildings. Unfortunately not a lot of green here represented by red. And we have the 100-meter resolution land cover. Can give you quite some information of what surrounds a city. We see quite a lot of buildup. You see only a little bit of green. And this is useful for some initial ID, but then we look at the 10-meter world cover map, and we already see some green popping up in the center, and we notice this high resolution is really valuable for a lot of research. So that brings us to the LCFM projects. We mainly had 3 goals. The first one is to continue the existing products. So those maps at 100-meter resolution with given classes, we have had a lot of positive feedback on them. So we'll make sure to continue them. They were from the year 2015 to 2019. So the next products will just continue building on those, providing maps for the years 2020 to 2026. But of course, we'll also try to enhance those. So as said, we'll also enhance those from resolution of 100 meter to 10 meters. But we'll also try to increase the temporal dimension. So these were yearly maps. From now on, we'll also release some monthly features, some monthly composites that we used in our own calculations, as this might prove very useful for research. Research never stops, we never stand still, so the accuracy is of course being improved, and we'll add some change mapping as well, which I will talk about later. And then last, we will extend the catalog as well. We'll provide 2 new products, namely a tree cover density map and a tree cover presence change map. That's not worldwide, it's only for certain areas, which I will show you later as well. But it's, for me personally, one of the most important products of this whole project. So these are the 7 main features that we'll be publishing. We have the land cover maps, land cover change maps, both on a 10-meter and 100-meter resolution. These are annual. But we've also introduced a new category, which is the land surface categories. These are monthly based categories, and we'll divide the land into a rough 6 classes. We use those as an intermediate step for the land cover classification, but once again we figured this might be really useful information for researchers for downstream applications, looking simply at water occurrence, snow duration, and change mapping. And as you see, these are monthly, so might also be interesting to see some events happening and noting those down. Next to that, I've had all the middle ones, but the ones at the side are also really important. There's the land surface features. So these are the features we use as an input to determine the land cover classifications. Those are both sub-annual as annual. So sub-annual, that means some monthly composites from Sentinel-2. We've had quite a lot of processing power in order to calculate these. We had some very advanced cloud masking in order to make sure our data is the highest quality possible. And we figured that, once again, all this processing power we've put into this might be very useful for other classifications. I talked about the WorldCover, and there being a lot of debates whether or not these classes are too restrictive or not. Given these features, we allow other researchers to define their own classification models and do their own classifications, so they can also build on all this processing power that we used to make sure all these calculations are as useful as possible for a broad range of research. And then we have the 2 new products, the tree cover density I talked about. You see a map of where these features will be calculated in the world. What makes these so important is that we use them for the European Commission in support of their new regulation. It's a regulation on deforestation-free products, which states that in the future products that will be imported in the EU must be deforestation-free, and companies have to prove this. They'll be able to prove this using these tree cover density layers, and that way, as Europe, we can stand against deforestation, which is, I think, a really important subject that I've heard in a lot of different talks already the past days. For the LCFM classification model, you can't have classification without models, you can't have models without training data, and once again, we try to be as open as possible, and we'll share these databases for other people to use for their models as well. Of course, here you are limited by the labels we used, but it might be very interesting should you have other features that you want to incorporate and train your own advanced model. Let's say you don't want only to include Sentinel-1 and 2. You wanted to also train on Sentinel-3, 5, or other data sources. Given these labeled data sets, you can train your own models as well, do your own classification once again. So all these steps, they adhere to really the open science principles. We try to publish these collections, but we also try to publish how we created them, so that researchers can recreate these themselves. To finish up the LCFM pipe, the LCFM line, I'd like to give you quite a timeline so you know when to expect these products. Currently, we're working on the 2020 results. There's still some validation and extraction to do. But we'll try to publish this as soon as possible once we know for sure that the quality is high enough. Then in the upcoming year, we'll work on the 2021 features, do some optimizations, some iteration based on early feedback we receive. And after that, we'll really start processing on a full time and produce for the upcoming years up until 2026, at which time you'll see here also, we'll try to produce those results on a near real-time basis. So as soon as we got the new data from the Sentinel missions, we'll produce new maps, which might be more important to event reactions. Now, all of this is very nice, but taking a step back, producing these maps There are quite some challenges that every researcher faces in remote sensing. In general, for big data, as soon as you want to process a lot of data that doesn't fit on a small Dell computer, if I would try it, probably explodes. You need a lot of budget, you need a new data center, you need to make sure your data quality is well enough, and you need to be an expert in algorithm performance to make sure your processing is as optimal as possible. Otherwise, you'll end up paying the double amount because you need to load in data twice. It's quite a lot of overhead for a lot of researchers. And what we've seen is that remote sensing researchers tend to become more and more computer scientists, whereas they should really focus on what has driven their research from the beginning. I have an example for Sentinel-2 as well. And then there's also another problem, is that different researchers in different institutions use different backends, different data sets. In Gilberto, his presentation, he also said something very nice, I think, is that in a lot of papers you find, you won't see the original code. And what I think happens is you can't share that code because there's so many local paths. Everyone codes in their own way, it's not readable. And if I would run it on my own computer, it probably wouldn't work because it's not ported to the right backend. Each backend has their own way of fetching all the data. And that, once again, is a lot of overhead and makes it really hard to share the processes used to produce any data. And that exactly is where OpenAO steps in. So OpenAO is to its core, it's a spec, it's a convention on different processes used for processing remote sensing data. And I'll just read the slide because I'm not sure if everyone can read the slides that well. That allows users to connect Earth observation cloud backends in a simple and unified way. So what it really tries to do is make this convention, it's an open source on GitHub, so you can see and contribute to all the discussions as well, that multiple backends can implement so that one user can do its processing on multiple backends, which might have multiple data sources. Let's say you have a process of calculating an NDVI, which you do on Sentinel-1 data on this backend, but you also want to do on Landsat data somewhere else. You can use these same process graphs and just port them to a different backend. It also makes it easier to share. Let's say I have this process in Europe, but we know that transferring data from Europe to America or the other way around is quite costly, some egress costs that apply to that. Simply send the process graph and they can do the processing themselves as well. So it's really about shareability of your process graphs. I think I've had most of these points. So being able to connect to different backends allows you to connect to many different pre-processed collections. It allows you to do some cloud computing, so my Dell doesn't explode, but I can make use of large clusters of data and processors that are managed by professionals doing that every day and not having to set up your own Kubernetes cluster and getting into that rabbit hole of documentation. It emphasizes the reuse of research and optimized processes, so we don't always invent the wheel a second time or a third or fifth. And the researchers can focus at the task at hand, not the data engineering. Leave that to me, I love working with it, so I prefer that you do what you're really good at and sometimes still goes over my head. And all of these contribute that OpenAO really tries to follow the open science principles like the LCFM project. It's all about shareability, openness, sharing all the progress you've made, so that's really important. Now, how does OpenAO work? At its core, I've seen the term data cube in a lot of different presentations the past days, but I figure I'll quickly explain it. What is a data cube? To its core, it's a multidimensional data structure. So you have your spatial resolution, you have the time resolution, and then you might have different bands, either the original ones or indices you've already calculated. And these data cubes are at the core of OpenAO because these are the cubes you apply your processes on. You have all these different predefined processes. I'll give an example like calculating an NDVI. You just give that your original data cube. Using the existing process, it knows which bands to take, or you might explicitly have to say, look at band 4 and 8 to do the calculation, and then it returns you a new data cube which you can use for your next processes. And that's how you build your whole process graph like you would as a kid with Lego blocks. A data cube is agnostic from the data files you're using, so both at the start as at the end. That's really dependent on the OpenAO backend implementation, which files you can use. So it doesn't matter if the original data is in JPEG 2000s, GTIF, preferably COX, of course, NetCDF, and your output formats, depending on what you do, can also be any data format you want. given that it's provided by your OpenAO backend, of course. And once again, you don't need any local processing because these data cubes make it really easy to do your calculations in parallel, which allows for the OpenAO backend to do it very performantly on large clusters, should you want to do very large calculations over tiles for years at a low cost. Now, all this OpenAO theory, I see I forgot to remove an animation. Now, all this theory about OpenAO at the center is really nice and well. What does it look like? A process graph, to its core, is basically just a JSON. And I hope that no one of you has ever had to manually write JSONs because you forget a comma and you're set back half an hour. So luckily, we have all the different clients, all open source. The most contributed to is, of course, a Python client. I think a lot of data scientists, including myself, prefer to work in Python, but there is also an R client. And I forgot to add that there's also a client within QGIS. I haven't used it myself, but I've seen that it exists, which is very nice. So these help you produce these process graphs. You send it through the OpenAO API to a backend that you choose. Now, LCFM is being produced on the Copernicus data space ecosystem, so I would feel bad if I didn't make a little bit of publicity for them. CDSE, in short, once again, try to use some abbreviations. They provide users worldwide with 10,000 monthly credits. So that's 10,000 credits you can use for your own processing free without ever having to connect a credit card at all. And that's quite a lot of processing you can do. To give you a reference, for processing a full S2 tile for a whole year takes about 150 credits. So that's a lot of processing, a lot of research you can do for yourself. And then if you have a certain research project, you can always approach certain funds to give you more credits. Contact VITO, contact me, I'll see what can be done. But it's really easy to gain more credits from them, from ESA, from the European Commission, for projects that really help a lot of places around the world. Another backend existing is Terrascope. It's at VITO. It's more focused on the Belgium environment. We have a very simple backend for the Google Earth engine. And I know that Sentinel Hub also has one, which is very useful for a lot of pre-processed Sentinel-1 data. So all these different backends make it easy. We have a federated backend as well, which connects all the different backends. But that's a lot of future talk. It's not used in practice already. Might be a subject for a talk in the next FOSS4G. Now, since we're at FOSS4G convention, I would feel bad if I wouldn't show kind of all the technologies used on such a backend. To be fair, I'm not a DevOps, but I can tell you a bit about all the different technologies. So we use Kubernetes for CDSE. I think we use a Hadoop cluster for our Terrascope backends. But each backend is free to choose their own implementation based on the hardware they provide. Of course, you almost can't do remote sensing without KDL. We use Keycloak and Traefik for logs and management. And a really important is Stack right here. It's been something that's been included more and more within the OpenAO environment with a new process called load stack, which you can just provide with a Stack API collection, do some filtering on spatial extent, and that allows you to load in almost any collection within OpenAO, given, of course, that the data hrefs are machine-to-machine readable. So a lot of collections, unfortunately, are built still with a manual login, like the Landsat on USGC. But a lot of collections are also freely available. Should this href just be readable machine-to-machine? OpenAO also supports S3, but since as an OpenAO backend, we won't pay for all the data that you're using elsewhere because that might become a very large bill. It's only with S3 with files that are openly available and free to use. But future development is planned a lot here. And I can't emphasize enough how much this load stack process and in general the Stack API functionality is helping to include also your own data, which I might show in a moment. Some OpenAO capabilities I want to put more of a spotlight on. There are quite a lot of user community examples. These are use cases, but also explain some of the functionality. Me, myself, as a programmer, I know I really should read more documentation, but to be fair, I often skip it, just look at the code snippet, copy-paste it, and hope it works. Well, these community examples do that exactly for you. You can just copy-paste a lot of the code, and it should work, of course. But they also give you useful use cases, which might inspire you, like, oh, maybe this research project can be done in OpenAI already. It also inspire you to see what you would like implemented in the future. And if you have an example of OpenAI yourself, we're more than happy to see PRs coming in and seeing how OpenAI is being used within the community. This example specifically was one of my first tasks at VITO. It's creating a parcel dilation notebook that uses a neural network. And that's something I also want to put in the spotlight is the usage of UDFs. So there are quite a lot of processes in OpenAI already, and you can do a lot with them. But sometimes you just want that really edge case of analyzing or using a neural network. In that case, you can also provide Python code where you get, at a certain point in your process graph, an input X-ray data cube, do whatever processing you want on it, and you just return a data cube so OpenAI can continue working on it, which once again extends the possibilities of everything you can do with OpenAI. Bugs still occur. Sometimes you make errors in your own code. Sometimes there is still a bug on OpenAI. There is a web editor where you can see all your different jobs at the bottom. At the left, you can look for your specific backend, which collections are available, which processes are available. And then this area on the right is the one I've been using the most. It's the logging area. Because of course, one downside of cloud computing, you can't use a debugger. You just send your job, wait for it to finish, hopefully finish, and if it's an error, it's sometimes hard to know what went wrong. So looking into these logs, you can get an idea of what went wrong. But we also have quite a lot of logs for performance optimization, where you can see, oh, out of these 500 minutes this job took, I can see that 400 went to Sentinel-1 pre-processing and all the rest is done pretty quickly. Then you might consider limiting the amount of Sentinel-1 data you're processing for your graph. So there's a lot of useful information there. And then lastly, and that's a really nice thing about OpenAI, I've talked a lot about sharing your code, but just saying you can share it doesn't really promote it. So there's also a OpenAI algorithm plaza. Should you make a process graph for something really specific, which you might think that it might be useful for other researchers, then you can publish your process graph here. You make it a bit agnostic for the input parameters, so someone can determine their own spatial extent, their own temporal extents, perhaps provide a link to his own machine learning models that are going to be used. And you have quite some research topics already. One of them is biopar, produced by VITO, which extracts certain biological parameters used quite a lot. And if those aren't pre-calculated for the years you want, or you want to apply that on, for example, Landsat, you can simply get your process graph from the algorithm plaza and plug it into your own process workflow. Now, let's quickly take a look at the time. I'll give myself 1 more minute of quickly showing you the web editor. Of course, I have to drag it to the correct screen. Let me see. There you go. And while this might look complex, this is the workflow for the LCFM monthly composites. And I'll quickly show you, without you having to read anything, what is there. So there's some load collections with a different color, one of which loads in the SCL layer, the scene classification layer, for cloud masking. And then we have 3 different data cubes for the different resolutions, 10 meter, 20 meter, 60 meter. We mask those all out. After that, you can't read it, but here is an aggregate temporal where we give it, okay, per month I want to take the median. I have to see that I don't say anything incorrect here. So you take the monthly median of all those filtered projects, and then we just save those as GTIFs and get those back to either my Jupyter notebook, or you can directly export it to an S3 as well, because if you're doing large calculations, you might not want to download everything, but just stay within the same cluster. So that is just a quick example I wanted to show you on how very complex research flows in the end can be seen on one screen. I can send you this, or I can send you simply the process graph as a JSON format. And that's the end of my OpenAO presentation. So quickly to sum it up, I've went over the LCFM products. All these products will be published as soon as possible. We're still doing some validation. And if you have any questions about OpenAO, whether or not it's applicable for your own research, how to get more credits, or if you're already using OpenAO and you need some help, I'm at this point really an expert. Come to me or send me a mail afterwards. Oh, and I want to add one more thing. In Gilberto's presentation, he had a challenge of how many lines of code does it take. Personally, I'm not a fan of lines of code because as a programmer, you can put everything in one line of code. So this morning, I was feeling energetic after the gala of yesterday. I tried to recreate a very simple process graph, which just does this for one band, the monthly composites, and some very simple cloud masking. It took me 15 minutes to create the first iteration, and I launched the job. Then my Wi-Fi canceled out, so I went over my presentation again. I saw I made a typo, so I had to rerun it, and then half an hour later, my results were in. So give or take, it took me 1 hour to create a very simple process graph to process all this data. I think that's a very nice metric. Thank you for your attention.